Hi everyone, this is going to be the lecture on binding energy per nucleon. So let's take a moment to review the objectives. Everything highlighted in yellow we have covered so far, so we're making really great progress on our objectives. Today we are going to be focusing on objective 2, can solve and define problems relating to mass defect and binding energy. Particularly, we're going to be calculating binding energy per nucleon and looking at a graph of binding energy per nucleon versus mass number, working on annotating that graph around stability of isotopes. We're also going to use our warm-up problem and our gear-up problem in order to review how to solve for the energy released in a nuclear reaction using 3 different methods. The first being looking at the mass lost from reactants to products and converting that into energy released. The second, calculating the binding energy for each reactant and product and comparing those to find the energy released. And the third one that's going to be really new today is using the binding energy per nucleon graph to determine the energy released. Okay, let's go ahead and dive in. For your warm-up, I'm going to give you this equation. First, I'm going to ask you, is this fission or fusion? And to justify your answer. Second, I'm going to ask you to balance the equation, specifically how many neutrons are needed in this or produced in this reaction. And then third, I'm going to ask you to solve for energy release using 2 methods that we already know. Method A is going to be the energy released in mega electron volts using the mass lost and therefore energy released. And method B, a little bit annoying, is going to calculate the energy released in mega electron volts using binding energy. So pause the video here. This should be a bit of a review, and then unpause the video to check your answers. Okay, so to start us off, this is a fission reaction. We are going from a big, heavy uranium-236 atom, splitting that into smaller, lighter barium-144 and krypton-89 atoms. I looked up the atomic numbers, these bottom numbers, number of protons, in the periodic table. And using the conservation of charge and conservation of mass, I was able to balance this equation, finding that I have 3 neutrons being produced. Those neutrons are super important because they can go on in order to strike another uranium atom and start to produce a chain reaction. Anyway, part 3 is asking us to find the energy released using 2 different methods. So let's start with method A. This is the first thing that we've learned this unit. This method is going to be to compare the reactant's mass and the product's mass to see how much mass looks like it went missing. Let me do that now. So here up top, I have the mass of my reactants, really just uranium, and the mass of my products, this being the rest mass of barium, this being the rest mass of krypton, and then I had 3 neutrons. I got the neutrons rest mass from my data booklet. And right off the bat, you can see that there is a difference in mass. My reactants had 236 and some decimals, and my mass of my products was 235 and some decimals. So we have quote unquote lost mass. I put quotes around that because we know that mass isn't really gone. That mass goes somewhere. That mass is going to be converted into energy that's released in the reaction. So let's go ahead and find what exactly that change in mass is. The mass of the products minus the mass of the reactants. And careful as you do these calculations, remember that we want to carry all the decimals through, no rounding until the very end. And my change in mass is coming out to be a negative number, just as I would expect. That's because the mass of my products is less than the mass of my reactants. So I'm going to take this supposed lost mass and turn it into energy released. Now I'm looking for energy released in mega electron volts. That tells me that I'm going to have to convert my mass into mega electron volts per c squared. So I'm going to use my data booklet for this conversion. And now I have my mass in very convenient units, mega electron volts per c squared. I'll use my equation delta E equals delta mc squared to take that lost mass and turn it into energy released. So delta E is equal to my delta M, 166 with a whole lot of decimals. That's in mega electron volts per c squared. So for that reason, I'm not going to plug in values for c and square them because it will simply cancel with my units. So I get a released energy of 166 and a bunch of decimals, mega electron volts. This is how much energy would be released in one of these uranium reactions. So that's method A. We're really looking at the change in mass of the products, seeing in the products versus the reactants, seeing that mass looks like it's being lost. That lost mass is really going into energy being released. Really want to emphasize here, we are looking at the whole reaction, comparing the reactants and the products. Now method B is saying to find the exact same thing, find the energy released in mega electron volts, but this time we're going to use binding energy. We should get a very similar answer to method A, but you're going to see method B is a little bit annoying. So our game plan for method B is going to be to find the mass defect and then find the binding energy of uranium, barium, krypton, and think through neutrons. And then compare the binding energy of the reactants with the binding energy of the products. So we are not going to be looking at the whole reaction to start. We're going to be zooming in on each individual atom. Let's take a look at uranium first. We know that uranium-236 is going to have 92 protons. We know that from the atomic number right here. And then subtracting 236 and 92 leaves me with 144 neutrons. So we are going to look for the mass defect of uranium-236. In order to do this, we need to take the rest mass of uranium. That's going to be the uranium nucleus already bonded together, already formed together. And then we're going to take that rest mass. From that, we're going to subtract the individual parts, our 92 proton masses and our 144 neutron masses. I'm going to have to head to the data booklet because I do not have those memorized. So here we are comparing the mass of the whole nucleus to the mass of each of the individual nucleons just on their own. This comparison is going to give us the mass defect. Of course, this mass defect came out in the units of U, so we're going to do a little conversion here to get this to mega electron volts per c squared. That's going to help me when I calculate my binding energy in just a moment. I'll use my delta E equals mc squared here. I'm going to put some subscripts here to remind me this is the binding energy and this is the mass defect. Using that, I'm going to solve for the binding energy for uranium. And I have approximately 1,743 with some decimals mega electron volts for my binding energy for uranium. What this means is that it would take 1,743 and some decimals mega electron volts to take a uranium nucleus and split it apart into its 92 protons and 144 neutrons. I'm going to repeat this process now for barium and krypton, and then we'll think through neutrons. Okay, so I've gone through, I have calculated the binding energy for barium and krypton. And so I have done all of my atoms. What I have been ignoring, though, are these neutrons. And so I want to think through the binding energy of a neutron. The thing is that a neutron on its own does not have binding energy. think about the meaning of binding energy. Energy that binds the nucleus together, that holds all of the protons and neutrons together in that nucleus, kind of like the glue. Well, if I just have 3 random neutrons that aren't bound to anything, they are not part of a nucleus, they individually will not have any binding energy. So what I'm going to do is I'm going to look at the binding energy of my reactants and the binding energy of my products, of course, ignoring those neutrons because there's no binding energy with them. And then I'll look in the binding energy, the change in binding energy from the reactants to the products, and the difference between that must be the energy released. And as I do that, I see that it looks like we have lost a binding energy of 166.723652 megaelectron volts. That must be going to the energy released as part of this reaction. Let's take a look. I want to point out that yes, method 1 looked at the whole reaction. Method 2, though, looked at the individual atoms first, and then looked at the whole reaction. So I know that both of these methods are using E equals mc squared. It's really important to get those parsed out in your mind. Take a look at our answers, though. Using method 1, we got an energy released of approximately 160, let's round to 167 megaelectron volts. And in method B, we also got to approximately 167 mega electron volts. If there was no rounding in either case, we actually would have gotten the exact same answer. As you can see, though, I would prefer method A over method B. Method B is simply a lot of work. And today what we're going to see, what we're going to be introduced to, is a new quantity called binding energy per nucleon. And for our gear up problem at the end of today's lecture, we're actually going to use method C, a new method, and you might like that one even better than these two. So as a reminder of some important definitions that we've learned previously, we have mass defect, the hypothetical amount of mass that would need to be released in order to form the nucleus. You should be thinking about comparing the mass of the separate nucleons, the protons and neutrons, with the mass of the nucleus as a whole when it is formed. It's going to look like mass has gone missing when forming the nucleus, but that mass has actually gone into binding energy. Binding energy is defined as the hypothetical amount of energy that would be needed to separate the nucleus into its individual nucleons, into the protons and neutrons. When you hear binding energy, you should be thinking about the glue that holds the nucleus together. This is related to the strong force that acts between protons and neutrons over small distances in order to overcome the electrostatic force that would normally repel protons from other protons. This is really key to forming a nucleus. And today, what we're going to do is take that binding energy and we are going to divide it by the number of nucleons. So we're going to take the hypothetical amount of energy that would be needed to separate the nucleus into the single nucleons, divided by the number of nucleons. You can kind of think about this as like the average amount that each nucleon would need in order to like give up being part of the whole nucleus. So we're going to divide by that number of nucleons. So I would like you, for a quick example, you're given the mass of krypton 81, a nice isotope of krypton, and your job is going to be to calculate the average binding energy per nucleon in the units of mega electron volts per nucleon. Pause the video here, give that a try, come back and check your answer. Okay, so far I have found the mass defect. Oops. I have found the mass defect up here, comparing my whole nucleus and the individual mass of the individual nucleons. I've used E equals mc squared to get to binding energy, being wise about my units. And I have a binding energy of this guy, approximately 685 mega electron volts. Of course, I'm not rounding my decimals though. And to find binding energy per nucleon, I'm simply going to take that and divide by the number of nucleons. In this case, the number of nucleons is 81, 36 protons and 45 neutrons. This gives me a final answer of approximately 8.4555, oh no, 4.555015 mega electron volts per nucleon. That would be my final answer. So we can calculate binding energy per nucleon. It's not all that different than what we've been doing, except that last step of dividing by the number of nucleons. But likely you're thinking to yourself, why should you care? Why would we ever want to do this? How does it help us? Well, the reason is the binding energy per nucleon, this calculation is connected to the stability of an element. How likely is it going to be to undergo fission or fusion? And so what scientists have done is they have done this calculation over and over again, and they have plotted it on a graph. Let's take a look at that graph. On this graph, you will see the binding energy per nucleon plotted on the y-axis. You will see the mass number, sometimes denoted just as a capital A, on the x-axis. The mass number, remember, is also the number of nucleons, the protons and neutrons. And so you see this kind of strange curve develop. And this curve has one thing that's particularly sticking out, this highest point right up here. This highest point is iron, or Fe, the isotope iron 56. Iron 56 with the highest binding energy per nucleon is going to be the most stable element according to the IB. Now, if you actually poke around on the internet, there are slightly different claims about the most stable element out there in nature. But according to the IB, we are going to go with iron 56 as being our most stable element. And now anything else on this graph, any other element, wants to get more stable. And in order to increase its stability, it might undergo fusion, if it's over here, fusion in order to increase its mass number, increase its binding energy per nucleon, and become more stable. And on the right side over here, these elements are going to undergo fission. They are going to split apart into other elements in order to become more stable. So when I say why should we care about that binding energy per nucleon? Well, it talks about stability, our most stable element being iron 56, and then helping us make predictions about what other elements are going to do in order to become more stable, in order to work closer, get closer to that higher binding energy per nucleon, getting closer to iron 56. Again, highlighted in orange here are the elements that will undergo fusion in order to produce products that are more stable, and highlighted in green here, undergoing fission in order to produce products that are more stable. So this graph can be really helpful when it comes to stability. And another thing that binding energy per nucleon is really good for is returning to our warm-up and using this graph as a way of estimating the energy released in a nuclear reaction. So remember, in that warm-up, we estimated the energy released by looking at the mass of the reactants and products. We estimated the energy released using binding energy of each individual, comparing the reactants and products. But now we're going to use a new method. For this same reaction, I want you to use this binding energy per nucleon graph that's listed below. And I want you to calculate the energy released from this reaction just using this graph. Pause the video here and give it a try now. So the first thing I've done using my graph is to identify where my reactants and products are actually located on the graph. So I was looking at the x-axis for the nucleon number. Uranium-236 has 236 nucleons. And so looking at that, I can trace that up to the point on this curve and over to estimate, and notice that this is an estimate, 7.4 mega electron volts per nucleon. I've done the same thing for barium-144, estimating 8.1 mega electron volts per nucleon, and krypton-89, 8.5 mega electron volts per nucleon. So you can already see, although this method is going to be a little bit faster, kind of a drawback is that we are estimating. So I'm going to take each of those values and use my number of nucleons in order to actually find the binding energy. It's going to go so much faster than before. I've started by looking at uranium-236. Again, my estimate from my graph was 7.4 mega electron volts per nucleon. I've multiplied that by the 236 nucleons, and I got the total binding energy, 1,746.4 mega electron volts. I'll do the same for barium and krypton. Okay, so I have my binding energy for all of my parts, uranium, barium, and krypton. Take a look at this last note that neutrons here do not have binding energy, and I should be more specific to say lone neutrons. By lone, I mean that these neutrons are not attached to anything. They are not bound to any nucleus. They're not bound to any other protons or neutrons. They are on their own, flying away. Therefore, they have no binding energy. So to find the energy released, I'm going to need to find the binding energy of my reactants, the binding energy of my products, and I'm going to look for the change in binding energy between the reactants and the products in order to find the energy released. And I get that there would be 176.5 mega electron volts of energy released in this reaction. Now I just want to take a moment and compare that back to method A and method B from our warm-up. You're noticing that method A and method B are both yielding slightly more precise answers, right? We're getting a lot more decimals here, and we're rounding a little bit less. As opposed to method C with our graph, we had to make some estimates, so that error kind of compounded and made it a little less precise. But you can also see that we didn't have to go through each individual mass defect and binding energy calculation like we did in part B. We simply had to look at our graph and multiply them by the number of nucleons in order to get to our binding energy. So method C, a little bit faster, kind of nice in that regard, easy to predict if it's fission or fusion, all relative to that most stable iron 56 element. But you know, it is a little less precise because it is an estimate. One recommendation that I have for you as you're working through IB problems is to mark up your graph just as I have done and make your estimate clear. You want to be as clear as possible in your thinking process so there are no questions about where your numbers came from. So to conclude, today we have calculated binding energy per nucleon, essentially just taking binding energy and dividing by the number of nucleons. We have looked at a binding energy per nucleon versus mass number graph, finding the stability of different isotopes undergoing fission or fusion. And then we have solved problems around energy released using 3 different methods to do so, thinking about the pros and cons of each method.